Howdy everyone, my name is Abdullah Al-Zamli and welcome to our presentation. This presentation is on a research that my team and I have been working on for the past couple of semesters. My team consists of Shabib Hayajne, Ward Al-Bashtawi, Luqman Qazim and Omar Ali. So this research is focused on investigating the coupled effect of pore geometry, viscosity ratio, and wettability on the dynamics of immiscible displacement in a porous media using the computational fluid dynamics approach. So the following slide 2, represents to you the table of contents of the following presentation. So I would like to start off this presentation by taking you through the introduction, introducing to you some of the concepts and terminology that would help you stay on track throughout this presentation. My peers then would follow on with some literature review and discuss some of the papers currently found in the literature that is kind of complementary to our research question. Of course, we're going to also discuss the objective or the research question, the main driving force for this research, our methodology and procedure of the experiment, and of course, finally, the results and conclusion, which is the most interesting part in our research. So I would like to start off first by defining what is immiscible displacement. So immiscible displacement is the displacement of one fluid of another fluid, and now these two fluids are immiscible. Basically, they cannot mix, they form an interface. A common example can be found in the petroleum industry when using water flooding in EOR. So what is EOR? EOR is enhanced oil recovery. It is basically the techniques and procedures utilized by petroleum engineers to recover the remaining oil in place in the reservoir when the natural drive can no longer produce oil at an economical rate. And one common type of EOR is water flooding. Now, when it comes to water flooding, water is injected into the reservoir to displace the oil in the reservoir. And as we know, water and oil do not mix. So this is actually a common example of immiscible displacement. Another concept that I'd like to describe is wettability and the heterogeneity of a reservoir. So wettability and heterogeneity. Wettability can be defined as the tendency of a liquid to spread on a solid surface. It is basically the affinity of a liquid to a certain surface. Now, in terms of wettability, surfaces such as rocks, for example, they can be classified into three categories. We have the water wet, the mixed wet, or the oil wet. Figure 1 below describes or shows and depicts some of the examples of what happens when we have a water wet surface, an intermediate wet surface, and a oil wet surface. They are usually classified based on the angles of interface or the angles between the fluid, which is the liquid, and the surface itself. So it is important also to talk about the heterogeneity of a reservoir, which is basically the variation of the reservoir properties with position or space. So this involves the regular reservoir properties such as porosity and permeability, and also the pore distribution and pore geometry, and the angularity of the pores as well. So I have talked about immiscible displacement, and then I have talked about concepts such as the reservoir or a porous media's heterogeneity and wettability. The reason I talked about wettability and heterogeneity is because these are major factors that actually affect immiscible displacement. And one of the major phenomena that occur or might affect immiscible displacement is actually viscous fingering. So what is this phenomenon? I have mentioned in immiscible displacement water flooding in EOR in the petroleum industry. Now, to use that example again, when water is injected to displace the oil, water has a lower viscosity than oil. Therefore, some of the injected water would tend to bypass sections of the reservoir and create uneven or fingered, let's say, structure or profile. This eventually lowers the sweeping efficiency and recovery of oil through the utilization of water because of its low viscosity. So this is one of the phenomena that actually can occur in immiscible displacement, and this can be shown in the figure to the right. So viscosity or the viscosity ratio between the two immiscible fluids in the process of immiscible displacement in a porous media is a very important factor to take into consideration.
At this stage of the study, we conducted an extensive literature review to understand the main factors that affected the efficiency of immiscible displacement. We studied wettability, viscous fingering, saturation conditions, and many more factors that are related to immiscible displacement. For wettability, which refers to the ability of surfaces to hold contact with liquids, it was found that wettability plays an important role in the Bohr scale dynamics of the immiscible displacement in porous media. Three different papers done by three different authors made that clear as shown over here. Now we move on to viscous fingering. Viscous fingering, which refers to the ejection of a more viscous fluid by a less viscous one, had a direct contact with immiscible displacement. A study made by Dr. Zhao asserted that a significant difference would be there on immiscible displacement whether the system was weakly oil-wet or strongly oil-wet. Dr. Zhao recommended studying wettability with more detail in this focus, which was also recommended by Dr. Zhang and Dr. Avram in two separate research papers. Now, after building a strong understanding from the literature review, the time has come to raise the research question. As shown over here, the main goal of this study is to investigate the effect of wettability, Bohr angularity, and viscous ratio on the Bohr scale dynamics of immiscible displacement using a computational fluid dynamic modeling approach in a heterogeneous media over a wide range of contact angles starting from 0 degrees to 180 degrees. In simple words, we would be studying immiscible displacement on different porous mediums, such as the ones shown over here. Later, we would change the medium's wettability, angularity, and viscosity ratio to reach a conclusion. The methodology to answer this question will be presented right now by my colleague Walt.
So, what was the methodology of this experiment? The methodology was done all using OpenFOAM software. In OpenFOAM, the solver used was Interform that solves the Navier-Stokes equations using the finite volume model. Now, the post-processing of the numerical results was performed using the ParaView, and the contact angle was measured between the oil and the surface, which was between 0 degrees and 180 degrees. There were two different viscosity ratios, and three different porous medias with different pore geometries. So, as stated previously, we used the OpenFOAM software to do the simulations. Now, with the OpenFOAM software, we used contact angles from 0 to 180 using 20-degree increments. And there are certain parameters that you need to input into the OpenFOAM software to do the simulations, which are the interfacial tension, the receding phase density, and the invading phase density. These values with their units are illustrated in the table above.
Moving to the most important part of this research, the results. On this slide, we study two important relationships. The relationship between viscosity ratio and oil displacement in porous media, and the relationship between contact angle or wettability and oil displacement in porous media. And before explaining the figure, we need to know that oil represents, red is oil and blue is water. And so, looking at the first relationship, the contact angle, as we move horizontally from left to right, the contact angle increases, meaning we move into a water-wet system. And that's why we have a lower oil saturation, meaning a higher oil recovery. And if we think about it, as we increase the contact angle, we move into a water-wet system. And a water-wet system likes water, so it will keep the water and push the oil, meaning that we have a higher oil recovery. And this is what we need as petroleum engineers. The second relationship is as we increase the viscosity ratio, meaning moving up, vertically up, we have more oil saturation and less oil recovery. And this is shown in the figure here, as we have more, more of red trapped in these pictures, and thus a lower oil recovery. And this is due to what we know, to what we refer to as viscous fingering. From the first set of results, where we studied the effect of wettability or contact angle on the oil displacement, we found that there's a strong control of wettability on the displacement of fluids. And oil recovery is a function of wettability with optimum recovery under water-wet conditions. Now, in the second set of results, we found that oil recovery is lowest in a dilated porous media, where oil is mostly recovered when it comes to the tight porous media.
These are figures showing the results gotten after the simulations was conducted to find the relationship between the contact angle and pore geometry in the different porous media, I mean the normal, dilated, and the tight core samples that we used. This figure also represents the behavior of the invading fluid when the porous media was water wet, intermediate wet, and also oil wet. The chart represents the relationship between oil saturation and contact angle at different porous media. Also, the graph shows that contact angle does not have any impact on dilated porous media, I mean porous media with wider pore throat, whereas contact angle have more impact on tight porous media compared to normal porous media, which means that more hydrocarbon will be recovered when we have tight porous media compared to when we have normal one or dilated porous media.
From the first set of results, where we studied the effect of floatability or contact angle on the oil displacement, we found that there's a strong control of floatability on the displacement of fluids. And oil recovery is a function of floatability with optimum recovery under water wet conditions. Now, in the second set of results, we found that oil recovery is lowest in a dilated porous media, where oil is mostly recovered when it comes to the tight porous media. From the first set of results, where we studied the effect of floatability or contact angle on the oil displacement, we found that there's a strong control of floatability on the displacement of fluids. And oil recovery is a function of floatability with optimum recovery under water wet conditions. Now, in the second set of results, we found that oil recovery is lowest in a dilated porous media, where oil is mostly recovered when it comes to the tight porous media.